Hamiltonian graphs are graphs that are similar to what we've looked at, but a little bit different. Comes from another mathematician, Hamilton, and this kind of came about the same time that Euler's work was ongoing, and they thought this was the coolest math topic ever. What we're talking about with Hamiltonian graphs is reaching all vertices. That's the point. Yesterday, it was reaching all the edges. Here, it's all the vertices. So from that last example we have, what don't we care about? Landforms or bridges? We don't care about the bridges anymore. We just care about meeting all the landforms. Getting on the islands, getting off the island. We're looking at that. We don't care about all the bridges. There's a puzzle that I want you to try right now. And I don't know if you knew this about me, but I like puzzles. And I have you've never seen my collection, but I have a huge collection of all kinds of puzzles. And I don't have this one, so I think I'll probably build it tonight at home. But what it is it's a piece of wood made out of pentagrams, slices, but they took golf tees, drilled holes in them, and they glued them on there, and it fits on a stick. And what the point is you take this string, and you're supposed to get to all of the golf tees once and only once. It's like drawing, like your iPad is way better than this. It's drawing this pentagram, or pentagon within a pentagon within a pentagon, connected, and you're going to try to get to each vertice once and only once, and then you're going to get back to the first one. Okay? So can you do it? So let me give you an example. So maybe you did something like this, and I'm just randomly doing this. I certainly hope that it doesn't work. Shoot. I just did it. Okay. Anyway, I think it can be done. I think it can be done. I just knew when I was just randomly doing it that I knew it was going to happen. We don't care about all the edges this time. We just care about those. So here's what a good math teacher would say. See if you can find as many solutions to it as possible. There you go. Yes?
You can repeat mentions. Is that what you're saying?
Yes. And I think I did, didn't I?
Oh, yeah.
Yeah, not really a stumper, is it? Wonderful puzzle. I got to see if I could build one. That would be so fun to have like a classroom set and everybody's doing that. That'd be really cool. So on the next slide, a graph is said to be Hamiltonian. The way I like to think of it is every vertex back to the original. That's Hamiltonian cycle, or just Hamiltonian. Kind of like Eulerian was an Eulerian circuit. They meant the same thing. But semi-Eulerian, or semi-Hamiltonian in this case, is you get to every vertex, but not to the original. Okay? No surprise there. So they have an example here, but we could start, I think, just about anywhere. I could do F, G, E, A, B, G, D, C, B, and back to F. That would be Hamiltonian cycle. You can come up with some other solutions like theirs. They did G, F, B, A, E, D, C, B, and then back to G, or C back to G. I shouldn't have. Let me try. So G, F, B, A, E, D, C, G. Oh, maybe in my example I did. I may have. So Hamiltonian is vertices once, Eulerian is edges once. Okay, so that's actually the super easy part of this lesson. The tough part are three theorems. Theorem 1, Theorem 2, and Theorem 3. Okay? Now, I'm going to break you up into 3 groups, and you're going to explain these to us. So, before we talk about the 3 theorems, let me show you how you're going to be using those. For the homework, it says state whether each of the following is Hamiltonian, also semi-Hamiltonian, or semi-Hamiltonian. Here's 1, 2, 3, 4, 5. This is K5. K5 means what? Complete. Okay. And is this going to be Hamiltonian?
Yes.
Oh, absolutely. So let's write the vertices down here. 1, 2, 3, 4. 1, 2, 3, 4. All these will be 4. Any vertices in here? No, there weren't any. And so, by the way, is this Eulerian? Yeah, because they're all even. And Hamiltonian, we're going to figure out the rules. You can just look at it and say, boom, 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 boom. Around the outside, that'll be Hamiltonian too. But let's see how things work, because now what you're going to do at the bottom here, using the Hamiltonian theorems, 1, 2, 3, can you show that this is true? Okay? And some of these it'll work, some of these it won't be working. So let's start with group number 1. Tell us about this one. Have somebody come up with me. We're going to look at theorem 1. We were looking at all non-adjacent vertices. So the example was if you looked at this one and this one down here, you have 1, 2, 3, 1, 2, 3, and that sum, 3 plus 3, is that greater than or equal to 6? It is, so that's fine. How about these two? Okay, now wait a minute. Those are non-adjacent, and this is 2 and 2, and so if, when you're looking at these, both of them, 2 plus 2, is not greater than or equal to 6, but you do have some that are, so we want to be careful about the sufficiency piece to it. So it says there exists a Hamiltonian cycle. So what you're, So what you're looking at there is you're looking at if you take the non-adjacent, take the degrees of the non, like this one's V1 and this one's V3. This is V1 and this is like V3. If that sum is greater than or equal to the number of vertices, you got it. Okay. That's 1. Let's try 2. Who's got 2? So for number 2, what we're looking at is taking each vertex, and each vertex has a degree of 1/2 over n greater, then there exists a Hamiltonian. Now, you could have some less, like this one here only has 2, and it does work on the outside. Okay, but we can play with this a little bit, and we could say, well, what if this isn't here, and you did one of those? Okay, is this going to be Hamiltonian? I think it is if we, well, this is 1, 2, 3, 4. This is 1, 2. This is 2, 2, 2, 1, 2. And there's 6 points. This 4 is a problem, isn't it? It's not. This is not going to make it Hamiltonian because you're going to have to touch this more than once. So that's what negates it. So we got to have all of the vertex, each vertex, greater than or equal to n. And you can have less, but for sure, for sure, if they're all greater than, it's going to work. Certain cases will be less. Okay, and then the last one, number 3. The recap for this third one is they showed where the formula came from, but essentially what you're going to do is remove one point, which will take out two edges or more, and they added two. And when you have at least this many edges, it should be Hamiltonian. This kind of does an overview just by knowing the edges, whether that's going to be Hamiltonian or not. And with the complex ones, this is a good idea. So with those three, you should be able to take these problems, A through H, solve them first, and then see which apply to which one. And please feel free to double check in the answers here. You can see this chart at the bottom. Like the first one, all three applied. For B, none of them applied. See how some apply and some don't? So that's kind of that sufficiency angle. And then there's some other Hamiltonian ones to check. And that's it for Hamiltonian circuits.